This is one section from chapter 20. This will also be covered in Chem 1B, but it's in our course outline of records, so we are going to cover it. And this is the half reaction method for balancing oxidation-reduction reactions. Balancing by inspection often doesn't work very well for these. They can be a bit of a handful. So just a quick review of what we covered on Tuesday. So oil rig is the mnemonic that helps us to remember what's oxidation, what's reduction, right? So oxidation is loss of electrons. That's the oil, O-L, O-I-L. And reduction is gain of electrons. Another way to look at it, oxidation is an increase in the oxidation state. Reduction is a decrease or a reduction in the oxidation state. And I use both of those ways of remembering because sometimes one works easier than the other. So if we look at this reaction here between calcium and water to form calcium hydroxide and hydrogen gas, there's no charges on anything. This is a molecular equation. But if we look at oxidation states, we'll find that the oxidation state of hydrogen in water is +1, and the oxidation of hydrogen in the product, being an element, is 0. So that's undergone a reduction. Calcium has gone from an element to a +2 ion, and so that has been oxidized. When this happens, mass has to balance. We have to have the correct number of atoms of each element on each side, but we also need to balance charge. The overall charge on one side has to equal the overall charge on the other side. And so the half reaction method, we break the equation into two half reactions, we balance them individually, and then we add them back together. So that's what we're learning today. So here's the written out procedure. The first step, which honestly I think is really kind of optional. It can be helpful, but it's not absolutely necessary. Assign oxidation states to all the atoms. Identify the substances being oxidized and reduced. That would be great to do, but it's actually not absolutely necessary. We're going to separate the overall reaction into two half reactions. One will be for oxidation, one will be for reduction. A homework problem might ask you to identify which is which, but you don't need to in order to balance the equation. Then we balance each half reaction with respect to mass. So first you're going to balance everything besides hydrogen and oxygen. Then you'll balance the oxygen by putting water molecules wherever they're needed. You'll balance hydrogen by adding hydrogen ions. Then we balance with respect to charge. Yeah, question?
Sorry, you just said homework, so I was just clarifying. Did we get the paper version of worksheet 5?
No, I'm going to give that to you. Yeah. So then we're going to balance with respect to charge. So we're going to put the electrons in there, and we'll see that one of those is gaining electrons and one is losing electrons because there's an oxidation and a reduction. And we want to make the sum of the charges on each side of the equation equal. They're not necessarily going to be 0. It could be an overall plus charge on one side and an overall plus charge on the other side. They just have to be equal. The next step is to make the number of electrons in both half reactions equal, and that's done by multiplying one or both half reactions by a small whole number. Then we add the two half reactions together, canceling out the electrons and anything else that we can, and then we should always double check that it's actually balanced. So those are the instructions for the half reaction game, right? So we're going to do some practice problems here. And on this first slide, I have sort of a, crib notes here, very brief idea of this is what we need to do. And the hardest part about balancing these things is remembering to do these steps. So it says balance the redox reaction in acidic solution. So the first step is to assign oxidation states. We'll do that for practice. What's the oxidation state on this hydrogen? +1, because it's an ion, so the oxidation state is the same as its charge. How about on CR? 0, that's an element by itself. Here we've got hydrogen, H2. That's an element by itself, right? There's 2 hydrogen atoms bonded together, so in order for it to be neutral and have oxidation states, it would have to be like one would have to be +1 and one would have to be -1. And you can imagine the arguing over who got to be what, right? So they're not going to have an oxidation state. They're just going to be 0. And then over here, this chromium ion. What's the oxidation state? +2. It's the same as the charge. Yeah, that's how you do it. The oxidation states, like so many things in chemistry, are really confusing and mysterious until you see how it's done, and then you're like, oh, why couldn't I see that before? You have to just get to that point. Okay, so the optional step number 1. Step number 2, separate into half reactions. So you'll notice that we have 2 reactants and 2 products, right? So we're going to split these up. I usually write the first one first. So we're going to keep our arrows lined up in the middle here. So I'm going to have H plus aqueous. And then I'm going to have another one with Cr solid. So each of these reactants is going to get its own half reaction, which makes sense because we see the hydrogen is being reduced and the chromium is being oxidized. And then what goes on the other side is the thing most like it, right? So it's going to be the H2, because no matter how you try to do it, you're not going to be able to turn hydrogen ions into chromium ions, right? So it's got to be the H2 up there, and it's got to be the Cr2 plus down here. That make sense? We're taking it apart. If we add these 2 reactions together, we're going to get the same thing, right? Okay, so separate the half reactions. Balance the half reactions with respect to mass. This is the kind of balancing we've been doing. So we look at this, and I have 1 hydrogen on this side and 2 hydrogens on that side. It's not balanced. How do I fix it? I'll put a 2 in front of H plus. So now I've got 2 H's and 2 H's. It's balanced. This other one, I have 1 chromium and 1 chromium. It's already balanced. I don't need to do anything. So next is balance with respect to charge. Because what's happening here is on this side, I have 2 hydrogen ions. That's a +2 overall charge. And on this side, I have 0. So that's not a balance, right? One of these is going to be losing electrons, and the other one is going to be gaining electrons. And it has to be the same number of electrons because, there's no electron bank where you can go and take a withdrawal if you want extra electrons. So I'm going to balance the charges now by adding electrons wherever I need them. So electrons have a negative charge. So this is +2 and that's 0. Adding electrons over here is going to make things worse, right? But if I add electrons over here, I can bring that positive charge down to 0. So if I add 2 negative electrons, now I've got 2 negative charges and 2 positive charges. That adds up to 0 overall and 0 on the right. Does that make sense? And then down here, I have positive charge on the right and neutral on the left. So I'm going to need to add my electrons over here. I added 2 because of this +2 charge, so that these charges are going to add up to the same as the charge on the other side. Okay? The next step is make the number of electrons equal. Well, this is 2 electrons, and that is 2 electrons. It's already equal. So what's happening here is the chromium is losing 2 electrons. Those 2 electrons are being taken by the hydrogen ions to make H2. The electrons are not going to show up in the overall reaction, but we have to think about them when we're balancing it. So I've got my electrons equal, and now I'm going to add the 2 equations together. So this is like the equal sign. So anything that's the same on both sides, we could say cancels out. Because this is getting essentially made, they're coming loose, and then they're being absorbed again. So they don't show up in the overall reaction. So I'm going to copy everything down. The order on each side doesn't matter. I tend to just follow the same order. So then we should verify. So look at the mass, hydrogen, 2 hydrogens, 2 hydrogens, 1 chromium, 1 chromium. Overall +2 charge, overall +2 charge. That one's good. Any questions? Yeah.
What if those 2 electrons weren't equal? What would you do?
So we'll see what happens. If these are not equal, then I'm going to multiply all the coefficients by a small whole number so that I can get them to be equal. So like if I had 2 and 3, I'd have to multiply so that I could get 6 for each. Any other questions? Here's another one. Let's practice oxidation states again. So these guys are just ions, right? So what are their oxidation states? Same as the charge, right? So this one's +2, and that one's +3, and this one's +2. But this one's weird, right? We have manganese and we have oxygen. Manganese is a metal. It can have a variety of positive charges, but we can't really, this isn't an ionic compound, it's an ion. So we're basically going to use the FUS 765 rules. And the nonmetal here is oxygen. And so what would oxygen choose for its oxidation state? -2, like it would if it was an ion, right? So the oxygen's going to be -2. What does the manganese have to be? Not +2, because there's 4 of these guys. +7. So there's 4 of those, which gives me a total of -8 charge. I want these 2 to add up to -1. So this one's got to be +7. A little bit tricky. So splitting into half reactions. So I'm going to have two equations down here. So here's the first element. I'll put that in the first equation. And I'll put the second compound or ion in the second one. And then the Fe2 plus is going to change into which of these products? The Fe3 plus, right? Sometimes it's not as obvious. And this manganese must turn into that manganese. So next step, balance for mass. One iron, already balanced. Here we go, one manganese, already balanced, but I have 4 oxygens here. There are no oxygens over here for me to put a coefficient on. So this is where the rules say balance oxygen by adding water. This is not some magical thing that we're suddenly injecting water. This is an aqueous solution. It's happening in water. There's water all over the place. Usually water doesn't take part in the reactions, but in redox reactions it does sometimes. So I'm going to add water to balance oxygen. So I'm going to put water on the other side, H2O. And to balance the 4 oxygens, I'm going to need 4 water molecules, right? So that's great. I fixed oxygen, but I introduced a second problem. Now I've got hydrogens that aren't balanced. So we're going to balance hydrogens by adding hydrogen ions. This is an acidic solution, meaning there are hydrogen ions around. So I'm going to put some hydrogen ions in here. And over here, there's a total of 8 hydrogens, right? So I'll put an 8 here. So I have 8 hydrogens on this side, 8 hydrogens on that side, 1 manganese and 1 manganese, 4 oxygens and 4 oxygens. Okay? Now we'll balance the charges, because neither of these has the same charge on both sides. So here I've got +2 and +3. Where should I put the electron? Over here, right? This side has a higher charge, so I'm going to add an electron to bring it down to be the same. And if we look at this in terms of oxidation and reduction, the iron 2 plus is being oxidized to iron 3 plus. And oxidation is loss of electrons. So what's happening here is that the Fe2 plus is losing an electron. Down here, it's kind of a mess. It's a little bit harder to look at. But we can just balance for the charges. So over here, I have a +8 and a -1. And so +8 and -1, that's a +7 on the left. And then over here, the water doesn't have a charge. The manganese here has a +2. So I've got +2 on this side. How can I fix that? This side has a higher charge. The only way I can fix this is by adding electrons. So I want to add enough electrons to bring this overall charge down to that. So I'm going to need 5. electrons. This was oxidation, loss of electrons. This is the reduction half reaction, where the electrons are being gained by the manganese. Any questions? Yeah.
Actually, never mind.
Okay, you figured it out. Awesome. What's the next step? We need to get the number of electrons the same. Because right now we have one iron 2 ion. It's losing 1 electron, but down here this has to gain 5 electrons. How does that happen? We need this one to be losing the same number of electrons that this one is gaining. So this is a least common multiple sort of thing. So here I have 5, and here I have 1. Well, this one's fairly simple. I can just multiply this top one by 5. If I have 5 of them, then I'll have 5 electrons, right? It's still balanced, because I'm doing the same thing to everything. And now we add them together. If we've done this correctly, the electrons will cancel out. I have 5 electrons on one side and 5 electrons on the other side. We did that on purpose. And then I'm going to copy down everything else. So I have 8 hydrogen ions and a manganese permanganate ion and 5 iron 2+ ions. And I'm going to get that was spectacularly bad planning. You kind of have to, double check yourself, because it's easy to forget somebody. Make sure that you've got everybody down, and then check at the end. So I've got 8 hydrogens, and over here 8 hydrogens. 1 manganese, 4 oxygens, 4 oxygens, 5 iron, 5 iron. Mass is balanced, and then for charge, I have +8 minus 1, so that's +7. Plus 10, right? So that's 17. And then over here, I have 2, and 5 times 3, 15, plus 2, 17 on both sides. Any questions? Let's do another one. What's the first step? Yeah, ideally looking at the oxidation states. And so let's practice, because I think we could use a little practice, right? That is the first step according to the book, so we'll go with it. So what's the oxidation state here of copper? 0. And here I have nitrate ion, NO3 minus. So then I think Fe765, fluorine, hydrogen, oxygen. Oxygen gets to pick what oxidation state it has. And so it's going to choose -2. Nitrogen's got to make up the slack. There's 3 of these. So all those oxygens together give us a -6. So the nitrogen has to be what? +5. Now, we've never seen an N5 plus ion, have we? Because they don't exist. This is one of those instances where it's not a complete transfer of electrons, it's just an unequal sharing of electrons. So over here, what's this oxidation state? +2. And then here we have NO2. So again, oxygen gets to choose. Oxygen chooses -2. What does the nitrogen need to be? +4. Because there's 2 oxygens, right? So 2 times -2 is a -4, so this has to be +4. Yes? How do I know that the oxygen is -2? That's a great question. So what we talked about was this Fa765. And I think of this as the order in which these nonmetals get to choose their oxidation state. How do we know what oxidation state they're going to choose? It's going to be the same as the charge they would have as an ion. So fluorine as an ion would be what? -1. And hydrogen as an ion would be +1. And oxygen as an ion would be -2. Group 7, -1. Group 6, -2. Group 5, -3. So assigning these charges should come to you. It's not going to be instant, but we've done that a lot. And you don't have to do all of them at once. You just have to do the one you found, right? But the order is what I always had a hard time with. So Fa765. Does that help? So we're going to split this into 2 half reactions. I'll put the copper on the top and the nitrate in the second equation. And so which of these products should I put here? The copper 2+, right? And then the NO2 must go down here. And that makes sense because these have the same elements in them, right? Next, we balance for mass, number of atoms. 1 copper atom, 1 copper atom, 1 nitrogen atom, 1 nitrogen atom, 3 oxygens, and 2 oxygens. We can't fix that with just coefficients. We have to bring water in to help us out. So I have 3 oxygens here and only 2, so that tells me I need to add a water molecule on this side to get the 3rd oxygen atom. Okay? We can do that because this is an aqueous solution. Well, that was the gas, but this is aqueous. There's lots of water. So that fixed the oxygen. Next, we balance the hydrogen with hydrogen ions. And what's good about that is it doesn't cause any more problems. So I've got 2 hydrogens over here. So I'm going to need 2 hydrogen ions over here. Why do we balance adding H2O and H+? Because the rules told us to is probably the best thing for now. But we have an acidic solution. There's hydrogen ions and water present in the solution. So now we're going to look at charges. I'm going to get this out of the way. On the top, I have 0 on the left and +2 on the right. So I can fix that by adding 2 electrons over here. And if we look at what's happening to copper up here, copper's going from a 0 oxidation state to a +2 oxidation state. that happens by copper losing 2 electrons. And so this ends up telling me that the copper loses 2 electrons and becomes copper 2+ ion. That's the oxidation. This is the reduction. We're going to be looking at electrons being gained. And so the oxygen did not get oxidized or reduced. It's still -2. But nitrogen went from +5 to +4, right? It gained 1 electron. So if I put electrons in here to balance, that it gained 1 electron, so here's my 1 electron. So here, the 1 negative charge, and here's another negative charge, and there's 2 positive charges. This side adds up to 0, which is the same as that side. Any questions? How did you do that? Or why did you do that? So the copper is losing 2 electrons. Down here, we have to arrange for those 2 electrons to be gained by something, right? We can't just pass off one and the other one, like, poof, disappears or something. That doesn't happen. If this is losing 2 electrons, then the reduction has to gain 2 electrons. Well, this is only 1, and so to get it to 2, we're going to multiply all the coefficients by 2. Essentially saying, well, I need 2 of these half reactions. So I'm going to have 2 there. This will become a 4. There's a 2, a 2, and a 2. It's still balanced for mass and charge because we did the same thing to everybody. Now we're going to add them together. I have 2 electrons on this side, and those cancel with the 2 electrons on the other side. That should always happen. And now I'm going to write down what's left. There's a lot of things. And then I can check it. So 1 copper atom, 1 copper atom. 4 hydrogens, 4 hydrogens. 2 nitrogens, 2 nitrogens. 6 oxygens, and here I have 4 oxygens plus 2 is 6 oxygens. And then if I look at the total charges, I have 4 plus 1s and 2 negative 1s, so that's positive 2 on that side, and I've got positive 2 on that side. It's all balanced up. Any questions? What if the solution is basic instead of acidic? We're going to go through the same process. We're going to add 1 step. So we're going to balance the hydrogens by adding H+, like we did before. But in a basic solution, we have hydroxide ions present instead of hydrogen ions. So what we're going to do is we're going to look at the number of hydrogen atoms we have, ions, and we're going to add the same number of hydroxide ions to each side. So that won't mess up the balance. So let's say we had 2 hydrogen ions on one side. Well, then I'd have to add 2 hydroxide ions. what do I get when I put 2 hydroxide ions and 2 hydrogen ions together? I get 2 H2O. So that's how I'm going to get rid of the hydrogen ions. Balance the redox reaction in basic solution. So let's just go over our oxidation states. What's the oxidation state for I minus? -1. Here I have, this is permanganate ion. What do I do here? The oxygen is going to be -2, and there's 4 of them, right? So that's -8. Overall -1 charge, so this has to be +7. We did that one already. What's the oxidation state for I2? 0. And here I have MnO2. This is an ionic compound. What's the charge on the oxygen? -2. And the charge on the manganese is +4. Because there's 2 oxygens. Okay, half reaction time. I minus, MnO4 minus. So here I have iodide ion, so I'm going to choose to put the iodine molecule on the other side. And this manganese product is going to go down here with the manganese reactant. What do I do next? Balance for mass. 1 iodine, 2 iodines. So I need a coefficient of 2 here, so that I have the same number of iodine atoms on each side. Down here, I have 1 manganese on each side, but I have 4 oxygens here and 2 oxygens there. So what am I going to do? I'm going to add water, and I need 2 of them to the product side, right? So I've got 2 oxygens from the water, and these 2 oxygens bring me up to 4, which matches the other side. Now I introduced a new problem with the hydrogens. So I have a total of 4 hydrogens here. So I'm going to add 4 hydrogen ions on the other side. Well, there's 4 hydrogen ions. So 4 hydrogens and 4 hydrogens. So I have the mass balanced. This is where we put in that extra step. So this is basic solution. So I'm going to look and see where I have hydrogen ions. I only have them right here. I'm going to add to both sides of this half reaction the same number of hydroxide ions. So I'm going to add 4 hydroxide ions on that side and 4 hydroxide ions on that side. I did the same thing to both sides, so I did not mess up the mass balance. Yes? I put 4 because it takes 1 hydroxide to neutral 1 hydrogen ion. So I want to get rid of all the hydrogen ions because this is a basic solution. It's not an acid solution. Okay. So however many hydrogen ions you have, add the same number of hydroxide ions to both sides. Now I want to simplify this a little bit. So hydroxide ions and hydrogen ions together make water molecules, right? So what I'm going to do here is, instead of writing those guys like that, I'm going to write 4H2O liquid. Okay? If we look at the mass, now I have 8 hydrogens over here, and I have 4 hydrogens plus 4 more, 8 over there. I've got 4 oxygens and 4 oxygens and another 4, 8. And there I've got 2 and 2 and 4 is 8. Yeah.
Since it's not acidic, where did the H plus come?
That's a good question. Since it's not acidic, where do the H plus come from? They don't, and that's why we put the hydroxide in there, is to get rid of them. Okay? From the water, we can get hydroxide ions in a basic solution or hydrogen ions in an acidic solution. So you could ask, well, why don't we just add hydroxide ions instead of adding the hydrogens first and then then adding the other? Because when you add hydroxide ions, you're adding hydrogen and oxygen. And if you're trying to use those to balance the hydrogen, it can get messy real fast. So we balance it first with the hydrogen ions, and then we essentially neutralize them by adding hydroxide. So now we need to balance for charge. So this one, I've got -2 charge on that side. So what should I do on this side? Add electrons. So I need 2 electrons, right? On the bottom here, a -1 charge. And over here, a -4. So in order to make that -1 and -4, I'm going to add 3 electrons. I'm just thinking, because this one's getting kind of messy, isn't it? And balancing this like this can get really confusing. And so I'm thinking to myself, why is it that this is not confusing to me? I think it's because when I look at MnO4, I sort of picture that as 5 marbles, right? There's the manganese marble, might be purple or something, and then there's the red oxygen ones, right? So those are sitting there kind of together. Here, I've got 4 water molecules, so I'm thinking 2 white, 1 red. There's 4 of them sitting there. And so when I'm looking at these, I'm seeing the number of atoms of each element just kind of grouped together. And then the electrons are just to make all the charges the same. Any questions? What do we need to do next? This one's losing 2 electrons, and this one's gaining 3. That doesn't work. We need to make those the same. Well, we can't change a 2 into a 3 using whole numbers. So we have to go to the lowest common multiple, which is 6. If I multiply this by 3, I'll get 6. If I multiply this one by 2, I'll get 6, and then they'll match up. Pardon me? Sorry. So this is one equation. I'm going to clean this up a little bit. Because it kind of looked like that guy was up with this guy. So this half reaction has electrons being given off. This has electrons being used. And so I can multiply the individual half reactions by different numbers. So I'm going to multiply the top one by 3 and the bottom one by 2. And I wrote that down because I find that if I don't write it down as I'm going across, I screw it up. So on the top, I'm multiplying by 3. So this becomes a 6. Multiplying by 3, this becomes a 3. I'm multiplying by 3, this becomes a 6. Okay? I had it all balanced. I'm not messing that up because I'm doing the same thing to both sides. It's still balanced. But now I've upped the number of electrons. So down here, I'm going to multiply everything by 2. So I multiply the electrons by 2 and I get 6. I multiply the waters by 2 and I get 8. I multiply this one by 2, I get 2 and 2. And I'm multiplying by 2, this is 4. Multiplying by 2, this is going to be 8. Okay? Lots of little steps, lots of places to go wrong. Now I'm going to add these together. Whoops. That was scary. We don't want all that to go away. Okay. Add them up. Ask me.
For the I2, like, because you were multiplying the top all by 3, so wouldn't that be 6?
This. So are these fair game for exams? Yes, they are. There would be like one of these, and it would be show your work so that you could get partial credit, you know, because maybe you just goofed up one little thing. Well, I want to give you mostly the credit for that. And I usually try to make it one that's not crazy hard. This is kind of a hard one. There was a lot of canceling out of stuff. There's others that are a lot easier and still tell me that you know how to do the process. So this is one of those things that you can be very successful in Chem 1A without mastering half reaction method of balancing redox reactions. This is something, though, that if you're taking 1B is going to come up again. Yeah, because we'll go over chapter 20 in 1B and we'll do this again. But the course outline of record says I need to teach this to you. And so a lot of those things, even if you don't master them, if you need them in the future, your brain says, I remember something about that. And then when you go to figure it out, you're not starting from zero, right? You've got some ideas stuck in your head. They might be kind of dusty, but you can get them out and you can figure it out. Okay? Any other questions? Oh, there's another one. I was hoping it was the end, but it's not. So let's skip the oxidation state part. What do? Make 2 half reactions. I just find it straightforward to Put the first one in the first and the second one in the second. And so this one with chlorine is going to go to the other one that has chlorine. And this one that has the chromium is going to go to that one. Now what do? Balance for mass. 1 chlorine, 1 chlorine. 1 oxygen, no oxygens. What do we add to balance oxygens? H2O. So if I add a water molecule, notice I'm leaving spaces here because I might have to put coefficients in there later. So here I've got my oxygen. It introduced hydrogen, so now I have to balance hydrogen. But we do that with H+, and so that one's not so bad. There's 2 hydrogens over here, so I will balance this by adding 2 hydrogen ions over there. That's the part that's really different from how we were balancing equations before. Before, we didn't put extra things into them, right? You had what you had and you just changed coefficients. So that's one thing different about redox reactions, is that water often participates in that, and so we ended up having to put those in there. Okay, down here, 1 chromium, 4 oxygens, and this is a 4 on the outside, 4 oxygens. This has 4 hydrogens. Yes? Why didn't we add hydroxide to the first one? Because I'm doing the same thing to both halves and then going on to the next step. So I'm going to fix the mass on this one, balancing oxygens and hydrogens, and then I'll go back and neutralize the hydrogen ions. You definitely could do it right there. So 4 oxygens, I need 4 hydrogens. So that's going to be 4 hydrogen ions. But this is in basic solution. So wherever I have hydrogen ions, I have to add an equal number of hydroxide ions. So I'm going to have 2 hydroxide ions here. And I'm going to do the same thing to both sides so I don't mess up the mass balance that I just did. This one has 4, so I'm going to add 4 hydroxides. And 4 hydroxides on the other side. Okay? We could leave it like that, but then we have an awful lot of cleaning up to do at the end. So we'll say, well, 2 hydroxides and 2 hydrogens makes 2 water molecules. So I'm going to rewrite that as 2 water molecules. I'm just combining them. And over here, I've got matching. They're always going to match because we did it that way. We added an equal number to the number of hydrogen ions, and so then I'm going to end up with 4 water molecules on this side. Mm-hmm.
Why don't you combine the top water and
That's a great question. Why don't we combine the top water and the bottom water? I was just going to ask you if you'd like to do that. Well, so we have water here. We have water on both sides for that one, and then we have water up there and water down here. So at the very least, we should take care of what's in this line together, right? So if I could subtract this water molecule here and get rid of one of those, right? So let's make sure that we didn't mess it up, right? 2 hydrogens, 2 hydrogens, 1, 2 oxygens, 2 oxygens. Okay? Then we need to balance for charge. Here I've got -1, I've got -1 and 2 negatives. So over here I've got -3, and over here I have -1. So I'll need to add 2 electrons to that side. Get -3 charge on both sides. Down here, I've got 4 and 1 is -5, and this is -2. So I need 3 electrons over here. So 3 negatives and 2 negatives makes 5. 4 negatives and 1 negative makes 5. And then what do I have to do? I need to make the numbers of electrons the same, so that this one is gaining the same number that that one is losing, because that's what happens in a redox reaction. The electrons are transferred from one thing directly to another. There's no middleman. So I'm going to end up with 6 electrons again. So I need to multiply the top by 3 and the bottom by 2. 2 times 3 is 6. 1 times 3 is 3. 1 times 3 is 3. 1 times 3 is 3. 2 times 3 is 6. Down here I'm multiplying by 2. 2 times 4 is 8. 2 times 1. 2 times 1. 2 times 4 is 8, and 2 times 3 is 6. So now we can add these guys together. I have my 6 electrons here and my 6 electrons over there, right? So those go away. What else can I simplify? Water? Mm-hmm. So I have 3 waters on this side and 8 on that side. So if I took 3 away from both sides, subtract 3 from both sides, I would have none on this side. So I'm going to subtract 3 waters, so those go away, and this becomes 8 minus 3 is 5. And there's one other thing that's on both sides. Hydroxide. I've got 6 of them on this side and 8 of them on that side. So I could pull 6 off from each side. I'm not changing the balance. I'm just getting some things off that teeter-totter. So I'm going to subtract 6 hydroxide ions from both sides. 8 minus 6 is 2. And then I'm going to copy everything down. then I'm going to verify. 3 chlorine atoms on that side, 3 chlorine atoms on this side. Oxygens, there's 3 here, plus 2 is 5, plus 8 is 13. Over here, I have 2 times 4 is 8, plus 5, also 13 oxygens. Hydrogens, I have 2 plus, this is 2 times 4, so I've got 2 plus 8, so there's 10 of them. And over here, I have 10 hydrogens, 2 chromiums, and 2 chromiums. And then looking at charge, this is -3, and -2 is -5, and another -2 is -7. Over here, I've got -3, and 2 times -2, -4, -3 and -4 equals -7. Yikes, right? Yeesh. That better be the last one. If it isn't, I'll make it. Any questions about that one?
Is there an easier way to write this step by step? I'm not gonna have any idea what I did looking back on these notes. All these scribbles, like I have like 5 different color pens and it's still
Right.
not.
Yeah, so the question is there a simpler way to do this? To write it out? I haven't figured out one.
No.
No. What's nice doing it on the iPad is that I can make things disappear, right? So I can really erase things and keep it from looking as horribly messy as yours probably does. And just looking at this, what I've written, that doesn't tell the whole story, right? So if you want to look at my work here, you really have to watch the video and follow through on what happened step by step. I would never give you one like this on an exam. That one's mean. I mean, it's mean. It's good, though, to practice doing those, right? Because then when we do the simpler ones, they seem easy, right? Sometimes they seem too easy, and then, yeah, you overthink. Sorry, I can't help you with that one.